Chapter 2. Chapter 2 case study beginning on page 22 has to do with the Tohoku earthquake in Japan. Now this earthquake was on a convergent fault boundary, which means that one crust slid below the other, which caused a tsunami, which then flooded the nuclear power plant and caused a nuclear meltdown. This is a very famous case study that could potentially be on an AP test. It has before actually been on an AP test. On page 24, you need to know a couple of items from this list. You need to know the first three from the Earth's crust and the first three components of the air. And you do need to know that they're in these proportions here, 78%, 21, and 1. And so the rest of the chart you do not need to know, but you need to know exactly what's on this sticky note. On this page, also know the definitions of isotopes, radioisotopes, half-life, and what radioactive means. So again, know those definitions. On page 25, know which bonds are where in a water molecule. Most of what's in this chapter is review from other science courses that you will apply to this science course. So you need to know that between water molecules, so this is one water molecule, H2O, so two H's and one oxygen. Within the water molecule, you have covalent bonds that attach oxygens to hydrogens. Those are covalent bonds. But then you have hydrogen bonds that attach water molecule to water molecule. So know the bonds. On page 27 and 26, it talks about water's chemistry. There are 4 properties of water here on page 27. So make sure that you know about cohesion and bonding and ice and all of that here on page 27. Know the 4 properties of water. And again, they are review from chemistry and even biology. On page 28, we have the pH scale, again, which is review, but we will refer to pH quite a lot in this class with soil and with water. You do need to know that on the pH scale, each number going up is 10 times the hydrogen ion concentration. So if you can remember what pH is it measures hydrogen ion concentration. And so when you go up from 2 to 3, from 3 to 4, from 5 to 6, each jump is 10 times the hydrogen ion concentration. So when you go from 5 to 7, that's actually 100 because it's 10 between 5 and 6 and 10 between 6 and 7. So you go 10 times 10 and you get 100 going. So you jump 100 times ion concentration between 5 and 7. You also need to understand that normal rainwater is slightly below neutral. And then acid rain is much below neutral. And we will review that in chapter 17. On page 29, you need to know what a hydrocarbon is. So a hydrocarbon is made only of hydrogen and carbon. That's why it's called hydrocarbon. And crude oil is a hydrocarbon, and petroleum products are made out of crude oil or other petroleum, and natural gas and coal are all hydrocarbons. So carbon, hydrocarbons, and carbon and our fossil fuels have created wealth in our modern lifestyle. We heat with fossil fuels mostly, and we create pollution from it. But first of all, whenever we burn a fossil fuel for energy, for creating electricity, for heating our homes, for cooking with even, we break the carbon bonds and release energy. So what happens is that when we burn fossil fuels or even wood, that carbon, which is broken, will connect with 2 oxygens and make CO2. And we're going to talk about this a lot this year because this is the essence of global warming. So some CO2 gets dissolved in the ocean and makes something called carbonic acid, which we will study in chapter 16. Some is taken in by trees to make tree tissues, and this is called sequestration. So photosynthesis takes carbon dioxide and makes oxygen. But there's not enough plants to absorb all of the carbon dioxide made from burning fossil fuels in our current world. And so we have some that stays in the atmosphere and traps heat and creates a warmer planet. And we will refer to this is basically the basics of global warming. Chapter 18 is really all about it and the science behind it, and you'll understand the research that's going into it in chapter 18. So that's our introduction to it. Going on to 31, you need to know first of all, you need to know this figure and diagram about potential energy, kinetic energy, and entropy. So make sure you read the examples in your book about kinetic and potential energy. You can also see here on page 30, you have your potential energy in the bonds of food and kinetic energy as we move around. You don't have to go roller skating to have, or rollerblading to have kinetic energy. You just have to, breathe basically, or walk around or move at all. Know the first and second laws of thermodynamics. We will refer to these often this year. Entropy is an increase in disorder. So when you change energy, you go from a more ordered state to a less ordered state. And so this is an increase in disorder. So you have disordered here. So you went from a nice ordered molecules in wood, and you broke this energy into heat and light, and then you increased in disorder. So we never lose energy. It just changes into different forms. So the first law of thermodynamics says we never lose energy. The second law of thermodynamics says it will change into a more disordered state. So we increase in entropy when we do change the energy source. Okay, you need to know the photosynthesis equation. Make sure you know that water is consumed. So we start off with, technically here, we start off with 12 waters and we end with 6, but we simplify the equation here, and so the waters are used up. And so we say that photosynthesis has a net consumption of water. You also need to know this equation as well. So you basically need to recognize the equations on a multiple choice test. And this is review. You learned this in biology class. So most of our energy on the planet comes from the sun, but we have some that does not come from the sun. We have the gravitational pull of the moon creates some energy, like tidal energy. And then radiation inside the earth powers plate tectonics, volcanoes, geothermal activity, and hydrothermal vents. And in our hydrothermal vents, we have chemosynthesis that occurs, and you need to know this equation. So the key to chemosynthesis is this sulfur. So anytime you see sulfur, which is S, then you know it's chemosynthesis, because the other two do not have sulfur. And so that's an easy way to recognize the chemosynthesis. Up here you can see pictures of geothermal activity. This is in Nevada, but Yellowstone National Park is famous for its geothermal. And then this is a chemosynthesis occurring at a hydrothermal vent deep under the ocean at divergent plate boundaries. And sulfur comes out of this vent, and the sulfur that comes out starts the food chain without the sun. So chemosynthesis does not need the sun to create energy. It uses sulfur, and it's special bacteria that do this process. All right, on this page we have our picture of the Earth, and we have the layers. So you need to know the core, the asthenosphere, the mantle, and the crust. And then you also need to know what the San Andreas Fault is down here. It's our fault close to us. That is a transform plate boundary. And here's our plate boundaries here on 35. So we have divergent, where the plates split apart. This happens under the water, except they actually happen on Iceland too, but that's the only place it happens on land. But rest of it's underwater in the Mid-Atlantic Ridge and the Pacific Ridge. And this is where your hydrothermal events occur in chemosynthesis. And then you have transform plate boundaries. Sometimes they're called strike-slip fault. And so again here, know all the plate boundaries and what happens. And then the Mid-Atlantic Ridge here for divergent is famous. Strike-slip fault or transform plate boundary is what the San Andreas Fault is, which is the one that goes through California. And so when we have a huge earthquake on the San Andreas Fault, the plates slide past each other. Then this are two types of convergent plate boundary. So I have here a sticky note telling you both types. So I have an arrow pointing to this one and an arrow pointing to this one. So oceanic crust is denser here. So when we have oceanic crust and continental crust, this one slides below, we call it subducting, because it's more dense and it makes this trench along here. However, if you've got continental crust and continental crust here coming together, they're the same density and therefore they push each other up and create mountains. This is what's occurring where we have Mount Everest in the Himalayas. So you can see that up here. These are the Himalayan mountains, and this boundary here is where the Himalayas are, and you have Mount Everest. And so these crusts keep pushing against each other to create taller and taller mountains. Here's the Mid-Atlantic Ridge, which travels all the way up here, and the only place that it's on land is up here in Iceland, and Iceland is extremely geothermically active. And then we have the San Andreas Fault, which is our transform, so these plates slip past each other. And then over here is a convergent plate boundary over here in Japan, and this is the one where one plate subducted below the other and caused that tsunami. So you can see that here. This is what happened off the coast of Japan. And one plate slid below the other, caused an earthquake, and then this plate snapped back and caused a displacement of water. Page 36. So you need to know what a volcanic arc is. A volcanic arc is what Japan is. It's also what the Aleutian Islands in Alaska are. And this is when one oceanic plate subducts beneath another, and magma pushes up on the other side to create islands. The water becomes displaced and causes a tsunami. You also need to know these terms. So now we're in the rock cycle and we have different types of rocks. Oh, I forgot one on 36. Know this picture and caption of how rocks turn into others. So igneous will turn into sedimentary or metamorphic, and then metamorphic can melt and turn into igneous. So they can all turn into each other. And it tells you how they turn into each other on that picture. And then there are some types up here. Igneous, Yellowstone, so granite's actually igneous. And then sedimentary. Sedimentary you can usually tell because it has stripes, except this one has stripes because this is gneiss rock, used to be sedimentary, but heat and pressure turned it into metamorphic, and that's why it has stripes. So here's our examples, the ones most likely you could see on your test. So igneous rock is magma that has cooled. Magma is basically lava. And granite and basalt are our most famous types. And then sedimentary rock has this process of lithification, which is layers. And then shale and limestone and coal, actually coal is a sedimentary rock. We will continue on with chapter 2 in the next video.